Okay, so this dumb little pick which side you start on and cross off everything until you hit a non-zero number works every time and helps you to know when something is a placeholder versus when it's actually part of the measurement, okay? So by that, what I mean is if you look at the first three numbers, if that was a measurement that was taken, those numbers could actually all mean the same thing, just with different levels of precision. So if I had a very poor measuring device, maybe I only knew that my grams, let's say, was around 500, okay? And if I had a better measuring device, maybe I would know it to a little bit better level of precision, 510, or maybe even more, 512, or maybe even more, and it's like 512.00320, okay? That would be the same number if we reduce the significant figures down to one sig fig. All of these would actually be the same number. They would all reduce down to 500, okay? So when we write 500 as just 500, that's what I mean by the zeros are just placeholders. They're not significant. They're not part of the measurement. They're just helping us know that it's 500 and not 5, okay? Another way you can do this is if a number is written in scientific notation, then all of the digits that are shown are considered significant. So if I were to rewrite 500 and I only wanted one sig fig, I could only just write 5 times 10 to the second, which is the same thing as saying 500. If I wanted to write the next one, 510, I would write that as 5.1 times 10 to the second. Or the next one, I would write it as 5.12 times 10 to the second. What about if I had a measurement that was 500.00? Let's say I knew it really precisely. I just wanted to communicate that I knew it really precisely, but that it was 500 almost exactly. The way you would write that is either just like I've written it with all of the zeros, and it's like, well, why did you write those extra zeros? Because I'm trying to communicate a level of precision there, okay? Or I could write it in scientific notation, but I would have to include all 4 of those zeros. Okay, so 500 does not mean the same thing in science as 500.00. So we're going to look at an image in one of these slides that has 3 different measuring devices. And after I did this in my last class, I was like, I wish I had one where it was the exact same volume, just in 3 different measuring devices. So unfortunately, it's not. But go ahead and scroll up to this picture here. And hopefully this is going to get across what I mean by the level of precision of the measuring device. So if it was a balance, like a scale, it would spit back, a digital scale would spit back the right number of digits that corresponds to the level of precision. So like the example I gave about baking, like my scale is just going to say 500 if I have 500 grams of something. A more precise balance might say 500.00 or even 500.0000. I'm thinking that's probably the most precise balance I've used is 4 beyond the decimal point. Okay? So that's nice when you're using something that's a digital output. When you're measuring liquids in a lab setting, you're going to be using some kind of glassware that has a level of precision associated with it based on how it was calibrated when it was made. So on the left-hand side, that's just a very rough estimate kind of beaker, okay? So it measures off the milliliters in units of tens. So 10 milliliters, 20 milliliters, 30 milliliters, 40 milliliters. So if I wanted to know, like let's say that I was doing an experiment and I wanted 25 milliliters for a particular experiment. Well, if I want 25 milliliters just roughly, this would be fine. I'd fill it up, I'd try to make it somewhere between the 20 and the 30, and that would be fine. If I was doing a very high level experiment, I would want a tool that was more precise than that. And as we go to the right, these are more precise measuring devices. So this one is good because it does include 25. So let's go with that. So this one, each of the milliliters is marked off on the measuring device. They don't all have to be labeled, but there's markings to indicate precisely where 36 is, where 37 is, and so forth. So on this one, it's at the bottom of the picture, but down here is where 25 is, and then like this is 26, 27, etc. So if I was using this to measure out 25 milliliters, it's going to be a lot more likely that I'm going to get 25 milliliters. I'm being very careful with my words here because they all mean certain things, but I'm going to get a more accurate measurement of 25 milliliters using this one than if I were to use that one. Okay, and then we can go to an even more precise measuring device. Now this one's only showing it in 3, 4, 5, but you could use something like this that went up into the 20s. And in this one, the markings are at every 1/10 of a milliliter. So 4 and 5 are here. And then in the middle there, this is like 4.1, 4.2, 4.3, 4.4, 4.5, 4.6. Okay? So we're going to know how accurate our measurement is a lot better with a more precise measuring device. So how does that translate into when we take a measurement? There is a very special way or standardized way that we use to communicate to the general population how precise the measuring device was. Okay? So the way that we do that is we write down every digit that we are sure of, and then we get one guess. Okay? So what do I mean by that? When I look at the first one, I know for sure that this water level is in the 20s, right? There's no question there. Here's 20, here's 30, so I know it's in the 20s somewhere. So the 2 that I write down as a, in the tens place, that is 20. I know that for sure. And then I get one additional guess. Not additional, but one guess. One additional digit that is a guess. So I might say 23. Someone else might say 25. We do try to standardize this a little bit by when we have a liquid, we read at the bottom of what's called the meniscus. So there's a natural curvature when you put water in glass, and you read at the bottom of that curvature. So like when I look at that now, I'm like, maybe it's 22, maybe 23, but like maybe 22. That's okay if there's some variation only in that last digit though. So when we talk about significant figures and we say that the number 23 has 2 significant figures, everybody that knows about significant figures should know that the 20, the 2, is known for sure, and that the 3 is a guess. And there is going to be some variation depending on who's reading that thing, whether they say 22 or 23. There's 2 sig figs though, one of which is certain and one of which is a guess. So this number up here, 5.213, if I was just given that number as a measurement, like someone said, oh, I measured out 5.213 milliliters, I would interpret that as they were sure that it was 5. They were sure that it was 0.2. They were even sure that it was 0.21, and then they guessed that last digit. Okay? So that's what's implied when you're given a number with a particular number of significant figures. So if the person doing this were to add a 0 there, that's not a good idea because now you're doing two guesses. You don't get to make two guesses, you just get to make one. So if you gave that to me, I would assume that you actually knew all of these and that this was a guess. And that's why you have to be careful as far as how many digits you write down in a laboratory setting. Obviously in class, we're taking data. We're not the ones doing the measurement. We're taking the data and we have to then interpret what does it mean or what did it tell us. Okay, let's look at these last two examples and make sure that they make sense why they're reported this way. So the 34.5, let me zoom in on that. So here's our water level, and this was 34, and this line was 35. Okay, so 30 is down here, 1, 2, 3, 4, 5. Okay, so there's no mistaking the fact that that is 34 something, right? So the 3 and the 4 are known values. Everyone in this room, if they read that, would read it as 34. The last digit, the point something, that was a guess. Some of you might think it's a 5, some might say a 6, I don't know, a 7 or an 8 even, depending on how you read it. Maybe you were like looking up and it was down here, or maybe you bent down and looked at it level. The point is, it's a guess, okay? So 3 significant figures, 2 that were known, 1 that was a guess. And then the last example here has them marked off at 0.1, 0.2, etc. So this here is 4.5 and this one is 4.6. Now this one's obviously a lot harder to see, but let's just say the water level is right there. Okay, so again, anyone who's reading this is going to say that it's 4.5 something because the water line is between those two marks. The question is, what do they say the something is? Do they say 5 or do they say 2 or whatever? Okay, so in this case, 3 sig figs again, one of which is a guess, the other 2 are known. So every time, you know, and your lab teacher can decide how strict they want to be on this. In a lab setting, you in theory would be responsible to use the correct number of significant figures when you make a measurement. On our side of it, we need to know when we're given a measurement how many significant figures it has, and then how we use that in a calculation. So we're going to do addition and subtraction first, because this example here is a really good use of that. So let's pretend we take all these liquids, this water, and we mix it all together, and we want to say what the total volume is. So I'm going to add those up. 23, 34.5, 4.52, and it comes up to 62.02 milliliters. Okay, if I were to say, what's the sum of these water, you know, these different water measurements, it is really deceptive of me to say, oh, it's 62.02, because I don't know that it goes out that far. Like, do I really know it to that level of precision? No, because I totally was guessing all the way back here that this was 23. Like, if I guessed 22 and you guessed 23, that's going to have a huge difference on this number, right? That's going to be, is it 62 or 61? So it's not really fair. It misrepresents if you give more digits than your least precise measurement. And that's the big takeaways. All the calculations we do, their number of significant figures or the place value, we'll talk about that in a second, is going to be dictated by the least significant measurement or the least precise measurement, okay? So in this instance, because when we do addition and subtraction, the rules are a little bit different than multiplication division, just because inherently when you're adding things, you're adding or subtracting, you're adding things that are alike. You're adding, like, you know, how many apples do I have? You're adding apples together or something like that. You're not trying to combine apples and people and dogs, okay? You have to add like things. When you're multiplying and dividing, those are inherently different things, like we've seen with conversion factors. You're like moving from one unit to another, Okay, so they have different rules associated with them. When we do addition and subtraction, we go by the place value. That's what limits our final answer. So in this one, which is our least precise measurement, it was only reported to the ones place. So we are only allowed to report our answer to the ones place. So 62.02 cannot be reported any more than just 62. Okay, so the big statement takeaway, and then we'll look at one more example and then have you guys do one, is that in addition and subtraction, it goes by the least precise measurement. The place value in that least precise measurement is what's going to dictate what your answer can be in. So instead of saying like the 10th place and the 100th place, because it's hard to say a TH, and the 1000th place, I'm just going to say like 1 beyond the decimal, 2 beyond the decimal, okay? So like this one goes 2 beyond the decimal, but that one doesn't have any beyond the decimal, so my answer cannot have any beyond the decimal. So let's look at another example of this. So scroll down to this page. Okay, so in these three numbers, now this is like a little trick you can use. I feel like, why would you ever use this? Because usually you're going to be punching it in your calculator, not like writing it down like a third grader would add up numbers. No offense to third graders. I prefer that they do it in their heads. It's all good. So you're going to go by the least precise place value. So this one goes 3 beyond the decimal, this goes 2 beyond the decimal, this goes 4 beyond the decimal. Our answer is going to be limited by the least precise, or 2 beyond the decimal. So when I add all these together, my answer can only go 2 beyond the decimal. So I'm going to end that as 5.41. And before I forget, I'm going to send the list around. Last class, I did not have the second page. So those of you that were like, my name's not on here, it's because I didn't have the second page. There's still one that I need to check why it's not showing up on here. But, okay, let's go ahead and pass that around. Okay, in this one, it's subtraction, but addition and subtraction are the same rules. So here, it's 1 beyond the decimal place. Here, there's 3 digits beyond the decimal place. So our answer is limited by 1 beyond the decimal place, the least precise measurement. And so it's 5.6. However, the next digit is a 7. If it's a 5 or higher, we need to round up the digit that we're, where we're cutting off, okay? So the 5.6 becomes 5.7. So I can only go 1 beyond the decimal, but I don't just like hack it off, because that's, it's not 5.6, it's 5.679. So I have to round that digit where I'm cutting off if it's a 5 or above. Okay, so that's 5.7. Okay, let's have you try an example on your own. This first one here, just the first one. You do not have to line them up. You can just do it in your calculator, but you're using the rule of places beyond the decimal. Ty, where's Ty? Ty White. Coincidentally not here, or just doesn't want to be picked out? You're on the roll. I just don't know why I didn't copy you on the roll. So it's all good. Okay, I would like the record to show that I said it was so cold, and now it's starting to feel a little stuffy. So I wonder if that was simply because there weren't 40 people in the room. So maybe I won't call facilities management now. Okay, so this is not the end answer. I just punched it in my calculator, and that's what my calculator told me. So, you know, you would think, oh, well, that's what I'll report. No, you have to go by which is the least least precise measurement. So the first one goes 1 beyond the decimal place. This one goes 3. This one goes 3. My answer then can only go 1 beyond the decimal place. So this is the digits that I want to maintain, but because the number after it is a 9, I need to roll that up to a 5. So 1096.5. Yep.
I got the same answer, but I'm confused on how it's only 1 pass and not 2 pass.
Because you have to go by whichever one is the least decimal place, not the number of significant figures. So I'm not sure if that's what you were looking at. She didn't say anything about that. But sometimes when we get to multiplication division, it's how many significant figures there are. And yes, and I can see why maybe you would do it that way. So just decimal places. So this one's 1 beyond, so our answer can only be 1 beyond.
So it's whatever the lowest.
Yes.
Okay.
Yes, the lowest number. So when I say least precise, I mean the lowest place value.
Thank
Yeah.
you.
Okay, so be aware that we were not looking at the number of significant figures when we were doing addition subtraction, because we are going to do that now, and I don't want you to get the two mixed up. So in addition and subtraction, we look at the place value and where it ends. When we move to multiplication and division, we're looking at the number of significant figures, like how many total sig figs there are. Any other questions on this one before I switch to multiplication division? Okay. All right. So let's go up to this example here. This is 2 slides up from where we were. So because multiplication and division are inherently a different type of calculation, like you would be using multiplication and division, doing something very different than just mixing certain measurements together, we go by the number of significant figures in each number. I was going to say measurement. They're all not necessarily measurements, but each number has a given number of significant figures, and whichever one has the least number of sig figs, that's what's going to determine the sig figs in the answer. So this one, 4, 5, and 2 sig figs. So our answer has to have 2 sig figs. So when they do the calculation, they cut it off at this point. It's not about the place value. And you can see that really easily here. Because like this one goes to the 100th place. But our answer doesn't. That's because this isn't addition subtraction. Okay? Multiplication division goes by the overall number of significant figures. So you need to first determine the number of sig figs and then make sure your answer has the same as whichever is least. So it's still whichever is least. It's just least number of sig figs, not least place value. So if I was going through these just to like remind you guys, that 0 is not significant, whereas these ones are all significant. So I've crossed out the zeros that are there just as placeholders. as like a reminder as to why those have the number of sig figs that they have. Okay, let's try one of these on your own. So it's this one now. So start maybe by just writing down how many sig figs each one of these has. Don't you sound like the biggest dork when you say sig figs? I think it makes you sound really dorky. Or nerdy. There's a difference between being a dork and a nerd, or a geek and a nerd. I don't know. My nieces and nephews have explained it. It's like science versus Dungeons and Dragons. Okay, so 4, 3, and 2, make sure you're okay with knowing that those have the given number of significant figures. Those are really nice because there's no zeros. If there's no zeros, it's very obvious how many sig figs there are. And our answer then needs to have 2. So whichever is the least number of significant figures, that's what your answer needs to have. So 55.32 times 4.31 divided by 12. So the answer comes out to be, oh, I love this one, 19.8691. Okay? But my answer should only have 2 significant figures. All done. My answer should only have 2 significant figures. So I want to go here, but that's an 8. The next digit's an 8, so I need to round up. So the inclination would be to write it as 20. But 20, as I've written it like a normal person, only has 1 significant figure. So I need to make sure that I indicate that that 0 is significant, and I do that by putting a decimal. So now I've given it 2 significant figures by indicating that that 0, I meant for that 0 to be there. It's not just a placeholder. The other way you could do it is you could write it in scientific notation, but you would just be writing 2.0 times 10 to the 1. It looks a little bit more official than just putting that decimal there. I don't know. Okay. I'm debating whether I should do the next problem because I did it in my other class because it was on there, but I was like, you're not going to have anything this hard on the test. So I'm kind of thinking we just skip it. And if you're curious, do it yourself and then come check with me if you don't know why. The reason why it's just a little bit harder, it's not like it's super hard, but it's just, I'm not going to give you stuff like this, is because you have to incorporate both rules. So you would have to first do the addition subtraction rule, get your correct number of digits, then you would do the rest of the problem using the multiplication division rule and get your final answer. Okay, so if you want to do that, by all means, go ahead and then check your work with me if you still don't understand. But I'm not going to do it together because I'm not going to do something like this on the test. Okay, so that's the end of chapter 1. As I sent out in that email, if you didn't get it, you should be checking your university email. That's a very normal thing to do. It's like check your work email. Check your school email, okay? So I sent out an email with just kind of some like tips as you're getting to the end of a chapter. It's like your first homework assignment. Some people are still feeling not super confident. So a few things. The first is like study groups are amazing. So someone that you're roughly on the same level with, but it's not a bad thing to have someone that's a little bit more comfortable with stuff. It's going to benefit them too. So don't think like, oh, it's like such a waste of my time to do a study group because I don't need help. First of all, we all need help. And second, you're going to just know the stuff way better. So maybe you were like an A- student and you were helping out a B- student. Maybe that lifts them up to a B, but guess what? It also lifts you up to an A because you're teaching them. And by teaching them, you get a very strong understanding of the material yourself. And so you're going to just do that much better. Okay? So you can talk to people in here. We have a nice big class. You guys could get to know each other. Your lab groups are like a really good way to do that because you're already interacting with them in a more relaxed setting. And then the other thing that I suggested is the John Jay Atrium. So if you guys don't know, if you go into John Jay through like those main doors and like the gym's over on your left, and you go through the second set of doors, and then there's like 2 hallways that go this way, and then in front of you, it looks like it's doors to an office, and there's a secretary's desk there. If you go through those and take a little bit of a jog, all of the science and I guess engineering, I don't know. I think all the science and engineering professors, all of their offices are like in a circle on the first and second floor. And then in the middle is like tables, couches, like just very chill study place that people will hang out and do science homework. So you could go over there when you're gonna do homework, and that way if there are other people from your class or from your lab class, you guys can work on it together, okay? So study groups. You need to look for other example problems. If you get to the homework and the examples that we did in class, if those weren't enough, then you need to go do other examples. You can do, like the one that I sent you was from the Pearson study area, I think they call it. So like on Pearson, when you click on the Access My e-textbook, if you remember, it pops up with 2 different links. The first one's to the textbook and the second is to, or maybe it's vice versa. One of them says study area. That link that I sent you is from the study area. So it is just like you go in there and you find the topic you're looking for. Conversion factors, dimensional analysis. That's the one I sent you guys. Okay? And he will walk you through an example problem and talk through the steps just like I do in here. Okay? You can always use your class notes, but obviously if I'm not like showing you step by step, that may not make sense later on. Okay? The other thing is don't underestimate the value of like printed words. So in the textbook, they always have worked examples. And what that means is it's like, I'm going to do this part of the problem, and I'm going to show you my work, and I'm going to get this halfway answer, and then I'm going to tell you the next step, and then I'm going to do the work. So what you can do is just take like a piece of paper and say, okay, this is the next step. I'm going to work the step on my own before I see what the answer is, and then I'm going to check my work. And then I'm going to say, do I know what the next step is? Oh, I'm not sure. So I'm going to ask what the next step is, do the work, check my answer. So it can let you go a little bit slower and more at like your pace rather than what a video would do, which is just keeps going and going. Okay? So if you're struggling with the homework, you need to see more examples before you can then do it yourself on the homework. That's my point. Those examples could be on videos or the textbook or with friends. I think that's all. Okay, so all of your work on that needs to be as much as you can do by 11:59 on Sunday night. Whatever you've done at that point, that's your score. So even if you get like 70% of the problems done, that's still great. That's a 70%, okay? That is much better than a 0. So do all you can, and then don't touch it after 11:59, because if you try to go in on and do additional problems on Monday morning, it's going to zero everything out because it doesn't let me tell it like, oh, give 10% off per day. Like that's how I do the reading assignments. If you do it a day late, you just get a 10% penalty. For whatever reason, Pearson is not set up for those dynamic study modules to let me do that. So if that happens once and you're like, oh, I just wanted to go back and review, then let me know and I'll reset it. But you really need to just be done with it at that point. Okay? All right. Any other questions? We're going to move on to chapter 2. We'll just get like a brief little introduction. Okay. So there's a bunch of practice problems that we're going to skip over. Scroll. These are all ones that I basically have in there for when we do review before the exam. So they're just there for my benefit later on if I want to use them. If you guys want to use them, by all means. Do I have an answer key? Probably not. Will I make one? It depends on my mood. Depends on how busy I am that week. So I bet I could dig one out of somewhere. As we get closer to the test, or if you're just really overly enthusiastic, you can ask. It just might take me a while to get it to you. Okay? All right. Looking forward, we're going to briefly start in on chapter 2 today, just so that those of you that want to start working on stuff can go ahead and do it. And then we have all week next week to do chapter 2. So Monday, Wednesday, Friday will all be chapter 2. And then a week from Monday, so after next week, that will be a review day, which we won't do any new material. You just need to, I won't take attendance, but like it's always beneficial to come. It's pretty much a time for you to come and ask questions, okay? And then the exam will be on Wednesday. So a week from next Wednesday is the first exam. Okay, in the Pearson assignment that you did last night for the reading, if you didn't do it, you can go do it now, and it's a 10% penalty. So go do it. But in the reading, when you first open the assignment, it says read 2.5 through 2.9. So make sure to look at those because I don't always assign all of a chapter. So the first half of this chapter is super fascinating. It's all the history of like how we went from stepwise through our model of the atom and it developed over time. We just don't have time to do it all. So I'm not going to talk about it. I'm not going to test you on it. It's very interesting though. This is like kind of a good side note about how science works. So I remember talking to this woman that she was just like very annoying. But at the beginning of COVID, you guys are probably too young to remember this, but like the recommendations kept changing. Like I remember a time when we were wearing masks outside, and I remember like taking, like my kids were pretty young, but I remember taking them like on walks and being like, we'd sit down on a bench and I'd be like, don't touch the bench. We need to sanitize your hands. Like there was just, we had no idea about stuff because the science hadn't really happened yet. So nature does its thing, whatever it does, and then we as scientists try to understand it. So early on, there were not very many recommendations, or they were wrong necessarily. And then as we got more information and the science developed, we had a better understanding of things. And so we were like, hey, you don't have to wipe your groceries down. Or it's okay to not wear a mask outside because the airflow is going to move those particles away. Anyway, this woman was like, see, scientists have no idea what they're talking about because first it was this and then it was that. And I was like, that's because science takes time and we make recommendations as we learn more about it. It's the same thing with the atom. Okay, we had a very different understanding of what the atom looked like early on. Was that wrong? Well, yeah, it was not as good as it could be, but the model we had, 100 years before this was a lot better than the model that we had before we even knew there were atoms, okay? So just because a model doesn't stay the same or it improves throughout time doesn't mean that the early ones were wrong. It's more that they were a stepping stone for us to better understand things. And even this model that we're going to talk about is not really what high-level science uses now because we have a different view of how the electrons behave than what we still teach you guys in freshman chemistry, okay? That's what quantum mechanics is an understanding of really the location and behavior and movement of electrons. And so we'll explain electrons in a particular way in here, and we'll kind of get into what we really think they look like and behave like in the second semester when we talk about quantum mechanics, okay? All right, so our current model of the atom is a very, very tiny thing, a drop of water has like 1 followed by 20 zeros. So I was trying to do this in my head in class, and I was like, I think that's like 10 million trillion atoms in a single drop of water. That's meaningless to us. Like our brains can't, even when we get to trillions of dollars of debt, I'm like, ugh, I don't know what that means, okay? It's a lot, meaning they're super, super tiny, okay? In that teeny tiny atom, now think of that atom as a baseball stadium, okay? So we've got a baseball stadium, and the single baseball in the middle, it's actually probably smaller than this, but the single baseball in the middle of the stadium, that's the nucleus, okay? So the atom is already teeny tiny, and then the nucleus is a very, very tiny portion of that atom. And most of the space in the baseball stadium is just empty space, okay? So in that baseball, there are protons and neutrons, and that is where the vast majority of the mass of the atom is concentrated. So on the next page, so I'll kind of flip back and forth between these two pages. There we go, that'll work. So these two particles are what are in the nucleus, protons and neutrons. And let's just focus on these two columns because we're not going to think about mass in terms of kilograms. That's just too hard to understand. So the protons and neutrons have a similar mass to each other. We say they're about 1 atomic mass unit. And the electrons are a fraction of that, 0.0005 compared to the protons and neutrons. So that baseball in the middle of the stadium is like a really heavy lead ball, way more than lead, but it's very concentrated. It's one of the most dense things there is, period. It is, not probably, it is. It is the most dense area that you could possibly have. Lots and lots of mass in a teeny tiny volume, okay? As far as charge, the neutrons, like the word sounds, are neutral. They have no charge. That's why it's listed as 0 down here. And the protons, they have a charge, and we give them relative charges, like so we can compare them to each other. So we say the charge on a proton is just +1. Okay, so we're going to use carbon as the example here. And inside, so picture the baseball again, the baseball inside the stadium. So inside of that baseball are 6 positively charged particles called protons. So I think those are supposed to be the red ones here. And in most carbon atoms, there are also 6 neutrons. So approximately 12 units of mass, 6 positive and 6 are neutral. And then out in the baseball stadium, we've got, let's think, ping pong balls because they're lightweight and a little bit smaller than a baseball. We've got 6 ping pong balls throughout the stadium, and those represent the electrons. Okay, so 1, 2, 3, 4, 5, 6. Each one of those has a -1 charge, so exactly opposite the proton, same amount, but opposite charge, so that the overall atom itself has no charge. So the atom itself is neutral because there's 6 positives in the middle and 6 negatives in that empty space of the baseball stadium. And that is roughly what we think the atom looks like. Okay, so what do you need to know about these particles? So this first point, the number of protons defines the element. What do I mean by that? Well, if I look back up at this picture, and I have helium that has 2 protons, and you guys all know what helium's like when you think of like a helium balloon, okay? That's helium. It is much less dense than air, so it floats. And then carbon, the reason they have a pencil is because that's supposed to be graphite. Like graphite is a example of pure carbon. Coal would be another one. Diamond would be another one. So it can take lots of forms, but straight carbon. So they have very different properties. And the number of protons is really what gives them their unique properties. So much so that if we change the number of protons, we call that atom something else. So I'm going to pull up in a periodic table. So here's carbon. Green, that's good. Here's carbon. And the little 6 up in the corner, that's what we call the atomic number. It is the number of protons. It is so special that we say it defines the element, meaning like if it has 6 protons, it is carbon. We can actually change the number of neutrons, we can change the number of electrons, and it's still carbon. But once we say it has 7 protons, now it's a totally different thing. It's nitrogen, and it's going to have different properties. I use the example in my other class of like carbon and hydrogen. That's like a main component. Okay, this is an oversimplification, but yeah, I don't even want to use the example now. But carbon, nitrogen, oxygen, those all have very different properties. You can even just think of it as like oxygen in the air versus nitrogen in the air versus like CO2. Those all have very different properties. So the number of protons is really what dictates the properties of that atom. 1 second, I want to get to the same point that I got to in the other class. Okay, we'll wait and talk about neutrons next class. But I do want to talk about electrons. So the electrons are going to match the number of protons, assuming that nothing else has happened to the atom. Okay? So if we have 6 protons and 6 electrons, we would say that that's neutrally charged. But what happens if something comes along and takes away one of those electrons? That atom now has one extra, it doesn't have an extra proton, it's missing an electron. And so we would say that it's positively charged. Okay, so if you lose an electron, the charge is negative of that electron, so the charge on the atom increases. It's 48, just for the record. I know that says 51. It's wrong. So when it's positively charged, we call that a cation, not a caution, a cation. If it were to gain an electron, so 6 protons and 7 electrons, then it would have a negative charge, and we call that an anion. Okay? So the number of electrons can change. It makes an ion of its original